We're going to start talking about representing functions using power series. We're going to start with one that we've already talked about several times before. This series 1 plus x squared plus x cubed, etc. That's the sum from n equals 0 to infinity of x to the nth power. We already know just by the formula for a geometric series, this is a geometric series with first term 1 and common ratio x, that is equal to 1 over 1 minus x. But that's true only when that common ratio, x in this case, has absolute value less than 1. Now, we're going to start playing with these functions and talking about how we can manipulate them to get other series representations for different functions. So if we know a formula, a power series representation for 1 over 1 minus x, if we substitute in x squared in place of x, we get 1 over 1 minus x squared equals, and then we put in here x squared in place of the x. X squared squared, giving us x to the fourth, x squared cubed for x to the sixth, etc. In other words, in place of x, we put x squared, and we get the sum from n equals 0 to infinity of x to the 2n. Now, when is that valid? Certainly not for all values of x. It's valid when the absolute value of x squared, because we're using x squared instead of x, is less than 1. But it's easy to see that if x is any number strictly between -1 and 1, then its square will have absolute value less than 1. In fact, these two are equivalent, so we could just normally write this as the absolute value of x is less than 1. In other words, these two series have the exact same interval of convergence. Which is the open interval from -1 to 1. Let's keep playing with it, see what else we can get. If from our original series here, we substitute minus x in for x, we get 1 over 1 minus x, which is exactly 1 over 1 plus x. So when we're putting minus x in for x, we get 1 plus minus x squared, which just is the same as x squared. And as you keep going, you get minus x cubed plus x to the fourth minus x to the fifth, etc. That's just the sum from n equals 0 to infinity of minus x all to the nth power, which we can write as -1 to the nth power times x to the nth power. Now here we would need the absolute value of minus x, because minus x is what we're putting into this series up top here, to be less than 1. But this is the same as, again, as saying the absolute value of x is less than 1. So again, we have the exact same interval of convergence for all three of these series. But now we'll do something a little different. In this previous series, 1 over 1 plus x, let's say we put 5x in place of x. So instead of 1 minus x, we'll have 1 minus 5x. We'll put 5x here, we get 25x squared. We put 5x here, we get the minus 125, that's 5 cubed, x cubed. And we keep going like that. And that will be equal to the sum from n equals 0 to infinity of just putting 5x in place of x. We'll have minus 5x to the nth power, or we can write it as -1 to the nth power times 5 to the nth power times x to the nth power. There are many different ways you might write it. Any one should be good. This one's very nice because this is written in the standard form of a power series, where this is our coefficient, c sub n. So the standard form of a power series has us writing the sum from n equals 0 to infinity of some coefficient c sub n times x to the n. Now here, when is this valid? Well, we put 5x in for x in this series, and in this series, what we have had to have absolute value less than 1. So here we need the absolute value of 5x less than 1, which when we divide by 5, says the absolute value of x has to be less than 1/5. In other words, the interval of convergence is this interval from -1/5 to +1/5. So just by playing with it, we've got several different series representations for different functions. Let's keep going. Here I'm looking at 1 over 1 minus x squared. We can look at the previous series, for the series we started with, for 1 over 1 minus x, which I'll write down again here. That's just 1 plus x squared, etc. when the absolute value of x is less than 1. And I'm going to just put x squared in for x, and we get 1 over 1 minus x squared is 1 plus x squared plus x to the 4th plus x to the 6th, etc. That's the sum from n equals 0 to infinity of x to the 2n. Again, this is actually the series we looked at before. I'm sorry. Yes, we looked at this one before. I'm just checking earlier. I'm not sure why. I think I was just repeating that here. Here, that's valid when the absolute value of x is less than 1. Let's continue and just change it a little bit and use 1 over 1 plus x squared again, in place of 1 over 1 minus x squared. Well, here we can just think of putting minus x squared in place of x in this series. 1 over 1 minus x squared is 1 over 1 plus x squared. So when I put minus x squared in here, we get 1 minus x squared plus x to the 4th minus x to the 6th, etc. And that's just the sum from n equals 0 to infinity of minus 1 to the n, x to the 2n. It's just like this one, but it has alternating signs. And again, we would need the absolute value of minus x squared to be less than 1, which is the same as the absolute value of x, less than 1. Now notice, in all of these examples, it is fundamentally important to tell on what interval the series converges. Because if we're going to represent a function as a series, we need to know when it makes sense. If you try to plug in an x that's outside of this interval of convergence, you'll get nonsense for the series. It will be a divergent series, and everything you write will start to be nonsense. Most of you don't want that to happen. How can we represent a function like x over 1 minus x squared? Well, we can think of this as just x over 1 plus x squared. We can think of this as x times 1 over 1 plus x squared. And I can think of multiplying that x into each term of the series. That's x times 1 minus x squared plus x to the 4th minus x to the 6th is just from the series above, plus x to the 8th, etc. In other words, we get x minus x cubed plus x to the 5th minus x to the 7th plus x to the 9th minus etc. And I can write that in what I'll call compact form, or sometimes we would call this summation notation, because we think of this as the sum from n equals 0 to infinity. In summation notation, this is the sum from n equals 0 to infinity. It's just like this series, only we're multiplying each term by x. So I'll have minus 1 to the n. To multiply x to the 2n by x, we just write it as x to the 2n plus 1. And it converges exactly when this part converges, because multiplying by x doesn't change that convergence. And so this will again require that the absolute value of x be less than 1. So we're going to play around with messing things up a bit more. I've repeated this series 1 over 1 plus x is 1 minus x plus x squared minus x cubed that we talked about earlier. That's just the sum from n equals 0 to infinity of minus 1 to the n, x to the n, and it's valid when the absolute value of x is less than 1. What if I put in place of x something like x minus 3? 1 over 1 plus the quantity x minus 3 is the same as 1 over x minus 2. And if I just put in x minus 3 in place of x's, I get 1 minus the quantity x minus 3 plus x minus 3 squared minus x minus 3 cubed plus x minus 3 to the 4th minus x minus 3 to the 5th, etc. In terms of the summation notation, this will be a sum from n equals 0 to infinity. I'll work off of this one. I have a minus 1 to the n, and in place of x, I'm putting x minus 3 to the nth power. Now you see, this is a power series centered at 3. All of these earlier examples were centered at 0. That's when you see this x to the n. That's the same as x minus 0 to the nth power. Those are the simplest to deal with in most cases, but sometimes you want to deal with a power series centered somewhere other than at 0. Now here's a question. For which values of x does this new power series centered at 3 converge? Well, we had just plugged in x minus 3 into this earlier power series, so we need the absolute value of x minus 3, putting in x minus 3 in place of x, to be less than 1. In other words, the interval of convergence which is the solution to this inequality, it's an interval of radius 1 centered at 3. So in this case, it's the open interval because that's the less than. It's the interval from 2 to 4. So this power series is valid only when x is between 2 and 4. Don't try putting in x equals 1 into this power series or x equals 0. Try to write down what you get if you put in x equals 0. You'll see you get a divergent series. Let's look at this exact same function, 1 over x minus 2, that we just talked about and for which we got a power series centered at 3. I'll show you a different way to get a power series representation for this function. Divide the denominator by 2 and pull that out. You can write this as, well, if I first just divide by 2, this is equal to 1 over 2 times 1/2 x minus 1. If I then pull out a minus sign, I get minus 1/2 instead of the 1/2 here, times 1 over 1 minus x over 2. Why do I want it in this form? Well, we know the power series for 1 over 1 minus x. I'll remind you of that. 1 over 1 minus x is 1 plus x squared plus etc. So the power series we have here, we have this factor of minus 1/2 in front. Then we have 1 over 1 minus x over 2. We just take this series and plug in x over 2. So we have 1 plus x over 2 plus x over 2 squared plus x over 2 quantity cubed, etc. That's just minus 1/2 times, I'll write it in summation notation. We have the sum from n equals 0 to infinity. We have x to the n here in the numerator, and then we're dividing by 2 to the n. I'll write that as 1 over 2 to the n. You could write it in many different ways. Here's 1 over 2 to the n times x to the n. If you want to put this minus 1/2 inside that, you could also write it as the sum of minus 1 over 2 to the n plus 1. That's putting the minus 1/2 multiplying by each coefficient here, x to the n. Here the sum is from n equals 0 to infinity. And we ask the question, for which x is this series valid, meaning for which x does it converge and equal 1 over x minus 2? Well, it converges exactly when this series converges when you've plugged in x over 2 for x. In other words, we need the absolute value of x over 2 to be less than 1, which is the same as saying the absolute value of x is less than 2. That says it converges on this interval from minus 2 to 2. This is the new interval of convergence for this series.